Let's do a physics problem. This one is a little complicated and maybe even wrong, but still it's going to be fun. So the idea is to look at an accelerating car, front wheel drive versus rear wheel drive. Okay, now, right off the bat, I'm going to make the assumption that we're going to have normal friction, right? So here's my car. I have a car of length L. It's a box. It's just a box car. Okay. It's a car of length L. It has a center mass up here that's a distance S from the front and a height H above the wheels. And then the wheels are separated by L, just like that. And it has a mass. And we're going to use some numbers. We're going to get numbers in there. But just imagine what's the difference, right? If I have a front wheel drive car, then the frictional force that I'm going to use, the frictional force is the coefficient of static friction times N1. This is for front wheel drive cars. Okay, and then for rear wheel drive cars, the frictional force is the max. We're talking about the max here. Okay, maximum frictional force is mu s times N2, where that's the rear wheel. Okay, so there's a bunch of stuff to get on here. Obviously, we're going to have to deal with rotational equilibrium and accelerations and fake forces. Let's just get started. Okay, so the first thing that we want to do, let's just say I'm going to start off with, I'm going to do an all-wheel drive car first, okay? Just so we can see how that would work. And I'm going to draw a force diagram for the all-wheel drive car. And that will help me use the reference frame of the car and fake forces. Okay, so here's my free body diagram for an all-wheel drive car. So I have my car, there's my two wheels. And then I'm going to call that N2. I'm going to call that N1. I have the gravitational force at the center of mass, mg. And then I have a frictional force. I'll call that F1 because there's two different frictional forces. And then this one, F2. Those are vectors. Okay. Now, that's it, right? Those are the only forces acting on the car, and that's going to make it accelerate. But how do I deal with the rotational motion or the lack of rotational motion, the torque in the car? And this is where we're going to have a problem. I need to use the reference frame of the car. And if I want to use the reference frame of the car, which is accelerating, then I'm going to need to add a fake force. So in general, if I have a non-inertial reference frame, I can say F fake, I'll write it as fake, is equal to negative MA frame. So if I want to use the reference frame of the accelerating car, I'm going to add a fake force that's equal to the negative of the mass times acceleration of that frame, which is the car, okay? So in general, if the car is accelerating this way, then I'm going to have a backwards pushing force. I'm going to call that FA because I don't want to use FF because FF is the frictional force. I've already used that. I can't use it again. So FA is the acceleration force, which is, just as wrong as fake force. But it's going to be useful because now I can say, okay, the net forces are 0, the net force in the x direction is 0, the net force in the y direction is 0, the net torque is 0. And that's what we're going to get. So if I have an all-wheel drive car, I actually don't need the torque. Okay, but let's just write down our 3 equations to see what that would look like. So here's my x and my y direction. So now I can say F net in the x direction is going to be equal to 0, right? Because I'm in the reference frame of the car. So that means I have this friction force plus that friction force minus the fake force. So it's going to be F1 plus F2 minus FA. And those are scalars because I'm in the x direction. I can do the same thing for the y direction. F net y is going to be 0. That one actually is fine. And this is going to be equal to N1 plus N2 minus mg, right? Because the two forces pushing up are the normal force, the gravity is the downward gravitational force, and that's that. Now for the torque, I'm going to go ahead and write this equation, even though we don't need it. For torque, we have to pick a point about which we calculate the torque. Remember that in 2 dimensions, we can write torque as RF sine theta, where r is the vector from the point that you want to calculate the torque, F is the applied force, theta is the angle between those two. In this case, let's just pick, if I pick that point, I guess that's fine. Let's pick this as the point O. Not a great point. I don't know. Let's pick this point. I'm going to pick this as point O. Okay, just because it'd be easier to, no, let's pick, I have that, let's pick this point. I can't make up my mind, right? That's my point O, so now I can calculate the torques. We're going to use the right-hand rule, so a torque that would want to make it rotate by itself this way would have a positive torque, and if it wants to rotate that way, it'd be a negative torque. That's my right hand. Okay. Oh, it's got dark. Okay, so let's just go through. These two forces are going to exert zero torque because they pass through the point of rotation. R is 0. So this force right here, mg, is going to have it wants to make it rotate that way, so it's a positive torque. And we can use this distance, the perpendicular distance of s. So it's going to be equal to mgs. Now the fake force is also going to want to make it rotate that way. So it's going to be positive, and that's going to have a torque arm of h. So plus FAH. And then I have this is going to be a negative torque into L minus into L, the length of the car. And then that frictional force is going to apply a positive torque, right? Because it wants to make, no, I'm sorry, that's a zero torque. Passed it right there. Okay. So you can see that the acceleration is going to affect both N1 and N2. However, notice up here, let's go ahead and use our model for friction. So I can say 0 equals friction force 1, which is the coefficient of static friction, times normal force 1, plus the coefficient of static friction times normal force 2, and that's going to be equal to the F times A. Right, I'm sorry, FA, the fake force, which is equal to the actual mass times acceleration. Now over here, I can actually factor out mu s out of there. So I get mu s, the coefficient of static friction, N1 plus N2, assuming they have the same coefficient of friction, and that's equal to the mass times acceleration. Now, in the y direction, you can see up here that N1 plus N2 equals mg, right, but from the y direction. So I can just put mg right here, and I get mu s mg equals ma. Oh, the mass cancels. Oh, the acceleration is the coefficient of friction times g. And so, ooh, that barely made it in the frame. So if you have all-wheel drive, we can model this as just a plain block, just going brr, and it only matters about the acceleration. We don't have to worry about all the torque stuff like that. But this is an important value right here, and I'm going to write it down. A-wheel drive. A is mu s times g. Because that's our limiting factor, right? The other cases are not going to have the same acceleration, because if you only have some of the wheels, you're not going to have as much friction, but you're going to have just as much mass, so the acceleration should be lower. And again, you know, cars get really weird. They do weird stuff. The coefficient of friction doesn't always work. That's why these drag racers have giant tires, because they can have coefficients of friction greater than 1. But we're going to do it anyway because it's a physics problem and it's fun. So, I mean, no one can stop me. I mean, you could try to stop me, but you're not going to work. Okay, now let's go to a front-wheel drive car. Things are going to get complicated. Okay, so front-wheel drive car. I'm just going to use my diagram up here so I don't make things too messy. That's my frictional force. That's my fake force. That's mg. And then that's my diagram right there. Okay, so I have N2, N1, mg, friction on the front tire, acceleration. Let's just write F net x is going to be equal to the frictional force minus the fake force. Those are the only two forces in the x direction. So the frictional force is the acceleration force. Okay, and in the y direction, these will never change, right? F net y is going to be equal to N1 plus N2 minus mg equals 0. So, yeah, we'll just leave it like that. Those are going to be the same. The only thing that's going to change is my torque equation. Let's go ahead and just right up here, I'm going to say the frictional force is mu s times N1, and that's going to be equal to Fa, which is m times a. And then N1, if I solve this for N1 up here, I get N1 is going to be mg minus m2, so I have mu s mg minus n2 equals ma. And I'm trying to find that a. Okay. So now what I want to do is to find an let's just leave this as Fa. Yeah. Because it's going to appear in the other places too. Now what I want to do is to get rid of N2. Okay. So we're going to apply a torque equation. I have N2 right there, so let's pick this point about which to calculate the torque, because then we will not have N1 in there, but we will have torque from N2. So torque net O is going to be equal to, okay, so the frictional force has no torque because it goes through the rotation point. The normal force, no torque because that's go through the rotation point. The weight, right-hand rule, wants to make it rotate this way. That's positive. So it's going to be mg, and then it has a torque arm of s. The fake frictional force, and we did this already, the fake frictional force is going to be Fa, it's going to be also positive, plus Fa times h. And then the normal force N2 here is going to make a torque of minus N2 L. And that's going to be equal to 0 because it's in rotational equilibrium. So let's solve this for N2. I get N2L equals mgs plus FAH. N2 equals mgs over L plus FAH over L. Now I can plug that in up here, okay? And you'll see that I'm going to get an expression with FA in there twice. So let's plug this in and multiply it through by mu s. So I get, where should I do this? I want to do it right there. I'm just gonna erase this part right here because it's sticking out too much. Yeah, I don't need that. So right here I get Fa equals mu s mg. I'm running out of room, aren't I? I'm going to run out of room. Okay, let's do it. Let's put it over. Ooh, okay, so I'm just gonna do it. I'm just gonna do it right here. This is weird. Let's just rewrite this. So mu s mg minus mu s times N2, which is this, mgs over L, mu s times N2. This is confusing. Minus mu s Fa h over L. Okay, I got it. Equals Fa. Now I can delete that stuff. Delete. In chalkboards, we call it deleting, erasing. So let's add this to both sides, and I get Fa times 1 plus mu s h over L equals mu s mg minus mu s mgs over L. And then I divide both sides by that. Okay. Fa is mu s. I can factor out the mu s mg. Mu s mg times 1 minus s over L divided by 1 plus mu s h over L. Now let's multiply top and bottom by L. You don't have to, right? But I'm going to. So I get mu s mg L minus s over L plus mu s h. Oh, that kind of cut off. Let's see. Okay, that's what I got before. So let's write that up here. And then I can divide by the mass, right? This is MA, so that mass goes away. So I get, this is front wheel drive, A, mu s g, L minus s, over L plus mu s h. Well, we should check some things, right? Does it have the right units? So mu s has no units, g is meters per second squared, and then I have length divided by length, because that again has no units. So I do get units of meters per second squared. So that's good. I kind of want to like take the limit as it turns into all-wheel drive. I'm not really sure. But what about this? What is mu goes to 0, then that's 0, that's 0. So it gets 0. So the acceleration is 0. You wouldn't be able to accelerate on ice, right? Okay. I think this is fine. Let's go and do rear-wheel drive car. So in a rear-wheel drive car, all we have to do is change this to here, right? There's a friction force over there. So this equation is the same. This equation is the same. This equation is in 2. So this is going to be in 1 minus in 1. So that's the same. Now, the torque equation is going to be different. So let's write down the torque equation. I'm going to put the torque equation up there. That way maybe I can kind of like save some space. But that's fine right there. That's all fine. We're gonna put in numbers, don't worry. I know you're like, hey, what happened to numbers? Numbers are going to be coming. Because we can change a whole bunch of stuff, and so we can do this in Python. Okay, the torque equation. Now we're going to do the torque about this point because we want to solve for N1, right? So you could do it the other way, but I'm going to do it right here. So that's my torque point O right there. So torque, I'll call it torque net. We know it's O. Okay. So let's just look. These two forces have no torque because they pass through the point. That fake force wants to make it rotate that way, so it's positive, and it has a torque arm of H. So I get FA H. This one wants to make it rotate this way, so it's going to be a negative torque. Now, that has a torque arm of L minus S, right? Because this distance is L, this distance is S. That's L minus S. So it's going to be minus mg L minus S. Got that. And then I just have this one, it's going to be positive, so it's N1 times L. And I fit it in there. And that's going to be equal to 0. Which that didn't fit. Okay. So let's solve this for N1. I get N1 is going to be equal to, I got to add that to the other side. So I have mg L minus S over L. I added that to both sides. I subtract that from both sides. Minus FA H over L. I think that's right. I made a mistake here before and it made me mad. So let's just keep going. I have the answer because I did it. I worked out beforehand. So if I make a mistake, I make a mistake. Okay, so now let's multiply by mu s. So I get mu s mg, and then I get minus mu s times N1, which is mg L minus S over L, and then minus that, so it's going to be plus mu S FA H over L equals FA. I'm scared. Okay, so now let's subtract this from both sides, and I get FA times 1 minus mu S H over L equals mu S, I can factor out the mu S mg, mu s mg times 1 minus mu s times L minus S over L. And now, again, I can multiply both sides by L, right? So this is just going to be the magic of a chalkboard. L gone, L gone. And then I divide both sides by that. And I get FA equals mu S mg. And then let's just write this as L minus mu S. L minus mu S L plus mu S S. I think I got that wrong in my other problem. That's fine. And then all of that divided by L minus mu S H. So my other way I did this, I got just S up here. But I think this one's better. May have made a mistake. Let's do it both ways. Okay, so this is to rear wheel drive. This is check, okay. A is, again, I'm going to divide by the mass, right, to get the acceleration. So I get mu S G L minus mu S L, which is L times 1 minus mu S. But that's fine. Plus mu S S. Well, I got too many mu s's there. What did I do? I did make a mistake. Okay. This is fine. I think that's fine. I added that to the other side. That's fine. Over here, I factored out the mu s. So why is that? That's not mu s right there. Yeah. Okay, so I do get what I got before. So now these l's cancel, and that mu s isn't there, so I just get s. Okay. That's what I had before, which may be wrong, but you know, you get the idea, right? It's the idea that really matters. So I have mu s g times s over L minus mu s h. That's what I got before. Okay, so I think it's right. Okay, so now I have 3 accelerations. Let's just check the units. Unitless, meter per second squared, distance divided by distance. So that works out. Okay, what I want to do is just, which one should have a higher acceleration? Well, it depends on all these factors, right? So let's just pick, let's pick a length of the car, a mass of the car, a coefficient of friction, and then calculate this stuff, and then we can change the variables up in Python. So that's what I'm going to do right now. I'm going to switch over here to Python, and we're going to make some graphs. It's going to be great. Yep, let's just do it. Okay, so switching to computer. Now I have a new setup, and it shakes a little bit, so maybe this is going to be a disaster, but sometimes you just have to have, see, look at that. This is a disaster. I wonder if I can make this not shake. See, the whole thing shakes. Well, let's just shake it, right? Just the video is going to shake. Not the other part. Okay, so the mass of my car is 1,000. Mu s, I'm just going to call it mu. Let's say it's 0.7. L is 3. I'm making up values here. S is going to be 1.5, halfway, just halfway. Okay, and then H, the height of the center mass. I'm thinking about a normal car, maybe like a meter, right? And do I have, G. Okay, now the first thing I want to do, we're going to change all these parameters, right? So I'm going to make the accelerations as a function where I give it mu, I give it L, I give it S, I give it H, and then it calculates the thing. So I can change all these parameters. So the first one we're going to call is all-wheel drive. Let's just call it all-wheel drive. All-wheel drive, let's call it a function. Def all-wheel drive. And we're going to pass to it all these parameters. Now, I like to pass them as temporary variables so I don't get things confused. So I'm going to pass it mu t for the temporary coefficient, lt, st, HT. G, we're not going to change. Okay. And then I'm going to calculate A all-wheel drive temporary. It's just going to be, I'm just going to type in the equation right here, which is just mu S times G. So it's mu T times G, and then we'll return that. Return A all-wheel drive T. And let's just try that out. All-wheel drive, let's just print it. Print all-wheel drive mu L S H. Let's just see if it works. This shaking thing's really kind of bothering me. Okay, 6.8. So it's definitely less than that. That seems right? Less than G. Let's do rear-wheel drive now. Def rear-wheel drive mu T LT ST HT. A rear-wheel drive temporary is going to be, now I'm going to type in this other equation, which is, oh, do rear-wheel drive, that's fine. Mu S times G, so it's mu T times G times S divided by L minus mu times H. And let's return that. And let's just change this to rear-wheel drive, just to see if it works. Okay, and it is lower than what we got before, so I think that's good. Finally, front-wheel drive. Def FWD mu T LT ST HT. You can repeat those temporary variables because they're only used in that function. I'm not a Python expert, you know that. Okay. AFDT equals, now I'm over here, it's mu G, mu T times G times L minus S, LT minus ST divided by L plus mu T times HT. Yeah, okay. And let's return that. LA FWDT. And let's just change this to F. Okay, so in this case, the front wheel drive is lower than the rear wheel drive. It depends on the location of the center mass. So let's do that first thing. Let's see what happens as I move S forward and backwards. So I'm going to start with S right above the front wheel and move it all the way to the back wheel, and let's plot what happens to the acceleration. I think that's probably the only graph I'm going to make because I'm already at almost 30 minutes. And then I'll give you this code, and then you can change things around however you want. Okay, so let's make a graph. G1 equals graph. Because this balancing thing's really bothering me, and I have a little. Well, don't worry about it. Graph. Title equals all-wheel. No, let's just do FWD versus R rear-wheel drive. X title. Now I'm changing the. I'm going to change on the horizontal axis. I'm going to change the center mass. So let's just call it X center mass in meters. I guess we should put the units. And then the Y title is going to be the acceleration in meters per second squared. And then I need this width 400, height 200, because I have a zoomed in graph and I want it to appear. Now that makes my axis. Now I need to make three things to plot. I'm going to plot all-wheel drive, rear-wheel drive, and front-wheel drive. And the all-wheel drive shouldn't change, but I'm going to plot it anyway. So FA is my all-wheel drive, and that's, G-curve color equals color dot purple. I like purple. And label equals all-wheel drive. F front-wheel drive is going to be G-curve color is color dot blue. Label equals front-wheel drive. And then FR, maybe you could have guessed that, G-curve color dot red. Label equals rear wheel drive. Okay, so I have my graphs, so I just need to make the graph. So let's go down here. I'm going to start off with S equals 0, even though I have S as something up there, it doesn't really matter. And then ds is 0.01. So I'm going to increase the S value. While S is less than L, right, because I don't want to have it go past the back wheel. You could, it doesn't say you couldn't. What I'm going to do is to plot my 3 accelerations. So FA dot plot, it's going to be my horizontal variables S. My vertical variable is going to be all-wheel drive mu L S H. And I already have values for L, H, and mu, right? Now let's do F front wheel drive S front wheel drive mu L S H. And now let's do the rear wheel drive. FR dot plot S rear wheel drive mu L S H. Now, here's the most important part. S equals S plus DS. If you don't do that, you'll be stuck in an infinite loop, and that's just awkward. Okay, let's run this and see what happens. Okay, I'm happy. So the all-wheel drive didn't change. As I move the center mass back, you'll notice that the front wheel drive acceleration decreases because you have less force on that front tire. The other one increases. So at this point right here, the acceleration from front wheel and rear wheel will be the same based on this calculation. Now, it does change with H too. It does change with the coefficient of friction too. So all these things can change, and you can change these parameters around and see what happens just as a fun physics problem. Okay, so, oh, look at this. Rear wheel drive is greater than all-wheel drive. I just accidentally figured that out. Does that even make sense? I'm glad I plotted that. I think maybe that's true, right? Because of the way the car wants to accelerate. Where's my car? Let's see if we can figure that out. Okay, so here's my car. So if the center mass is way back here, then that torque from the fake force is actually going to push back on those tires even more, right? And so you may get a larger normal force than you would. Then the normal force is larger than just the weight, I guess. Oh, you know what happens? Aha, I know what happens. That's the point that this normal force on this side actually lifts up. I suspect that's when the car lifts up. And so you're actually pulling down because I didn't tell it not to. So that's pulling down, which increases the normal force back here too. So that's the point when the rear wheel gets too far back, it actually tips up. So I suspect that at that point where the rear wheel drive acceleration is equal to the all-wheel drive acceleration, that's your wheelie point. Okay, so that's it. Fun problem. I had fun. Thank you for joining me with this problem. I'll put a link to the code down below, and that's that.